Hello, everyone. Welcome to the ILTA Physics Problem Solving Lecture. Today, we're going to work through various problems related to rotational dynamics. Rotational motion is, in a way, motion that is moving yet staying in place. It expands our previous way of thinking, where we viewed motion only as a change in position into a change in orientation. For more details on this, please refer to my previous theory lecture. We'll be looking at problems regarding the inertial mass of several objects in relation to rotational dynamics. We'll also solve problems applying Newton's second law to the relationships between angular position, angular velocity, and angular acceleration. All right, let's briefly summarize the core concepts of rotational dynamics. Rotational dynamics problems can all be solved using just a few formulas summarized here. However, you do need practice to accurately understand the problem and know which formula to apply. In terms of rotational kinematics, there are only three parameters. First is angular position, defined as the ratio of the arc length traveled to the radius. Second is angular velocity, which is the rate of change of angular position over time. Third is angular acceleration, defined as the rate of change of angular velocity over time. And angular velocity and angular acceleration have a proportional relationship with respect to time. A formula frequently used in actual rotational motion problems expresses the angular position over a certain period using angular velocity and angular acceleration. If time isn't given, you can also calculate the angular displacement using the final angular velocity, initial angular velocity, and angular acceleration. Keep in mind that these equations correspond directly to the formulas used in linear motion. If a problem mentions torque or force as a condition for rotational motion, you must keep these two equations in mind. First, in rotational motion where an external force is applied, torque is calculated as the product of the distance from the rotation axis and the perpendicular component of the applied force. Also, if the geometric shape of the rotating object is given, torque can be calculated as the product of the object's moment of inertia and its angular acceleration. In these cases, the process of calculating the moment of inertia for the given object is naturally included. Most problems ask about the relationship between these two ways of expressing torque. Let's practice how to apply these types of problems in the following examples. Finally, there might be questions about tangential velocity or acceleration in rotational motion. Once you've found the angular velocity and angular acceleration, you can easily find the tangential velocity and acceleration using the following relationship. These are the only formulas used for rotational motion problems. Now let's practice how to use and apply these formulas through some actual problems. Problem number 48 is about accelerated rotational motion, specifically bringing a rotating bicycle wheel to a stop. The problem description is a bit long, so please pause the video for a moment, read the problem yourself, and think about what it's asking. Did you read it and understand the content? Can you visualize which formulas to use and how to apply them? Then let's look at the problem together step by step. The moment of inertia of a bicycle wheel, like the one in the picture on the right, is 0.097 kilograms meter squared. To check the wheel alignment, a technician spun the wheel at a speed of 5 revolutions in 2 seconds. Now, a brake pad is used to stop the rotating wheel. This pad is located 7.1 centimeters from the axis of rotation, and it stopped the wheel in 1.5 seconds. Here is the question. What is the magnitude of the frictional force acting on the rotating disc? Generally, when a problem description is long, it becomes much easier to understand if you separate the conditions regarding the rotational motion from the information about the object itself that isn't related to the motion. In this problem, the conditions shown in red are about the rotational motion, and the conditions in blue are information about the object itself, unrelated to the motion. Since a force is being applied to the rotational motion via a brake pad, you should first think of the two formulas for calculating torque. Specifically, the relationship calculating torque as the product of force and distance, and the one calculating it as the product of the moment of inertia and angular acceleration. From a kinematic perspective, there are two conditions for the rotation in this problem: the condition for the rotational speed and the condition for stopping the rotation. First, since it said the wheel rotates 5 times in 2 seconds, the angular velocity of the bike wheel is 15.71 radian per second. And since it said this rotating wheel was stopped in 1.5 seconds, the angular acceleration is minus 10.47 radian per second squared based on the definition. The reason the angular acceleration is negative is that it acts in the direction of slowing down to a stop. Now we're going to find the torque of the rotating bicycle wheel using two different methods. Torque can be calculated as the product of the moment of inertia and angular acceleration, which gives a value of $1.16 Newton meter. Also, torque can be calculated as the product of the distance from the rotation axis and the applied force, and in this case, the applied force is the frictional force between the brake pad and the rotating disc. Therefore, using the torque formula, the frictional force is calculated to be 14.3 Newton. Although the description is long and the conditions seem complex, this problem is ultimately solved by finding the angular velocity and angular acceleration, and then applying the two torque equations. Problem 49 gives the angular velocity and angular acceleration as conditions and asks you to calculate the torque. It's much simpler and more direct than the previous problem. It's asking for the torque required to make a disc of a given mass and size rotate at 1800 RPM in 4 seconds. There is only one condition for the rotational motion, reaching a rotational speed of 1800 RPM in 4 seconds. Since the final angular velocity is 1800 RPM, converting this to radians gives 188.5 radian per second. And the disc started spinning from rest, so the angular acceleration is 47.125 radian per second squared by definition. Now, to calculate the torque that creates this rotational motion, we can first calculate the moment of inertia using the mass and size of the disc. Then, the final torque is calculated as the product of the moment of inertia and angular acceleration, resulting in 0.047 Newton meter. This problem can be solved simply by using the several formulas we summarized earlier in the proper order. Problem 50 gives the rotational torque of a spinning propeller and asks for the time it takes for that propeller to reach a speed of 2000 RPM. Unlike the previous problems, this type gives the torque and asks for the time using angular velocity and angular acceleration. First, the propeller can be thought of as rotational motion with one end of a thin rod as the axis, as shown in the picture on the right. Therefore, the moment of inertia can be calculated as $53.33 kg meters squared using the formula. Plugging this value into the torque formula, the angular acceleration becomes 9.375 radian per second. Now we are going to use the kinematic equations. Since the final speed is 2000 RPM, converting it to radians gives 209.44 radian per second. Using the relationship between angular velocity and angular acceleration, the time it takes to go from rest to the final angular velocity of 209.44 radian per second is calculated to be 22.34 seconds. Again, the problem can be solved by appropriately using the formulas we summarized earlier. Problem 54 is about rotating a huge stone with a mass of 8,200 kilograms and a radius of 90 centimeters, as shown in the picture on the right. As you can see in the picture, water comes out from under the heavy stone to minimize friction, allowing such a heavy stone to be rotated with a reasonable amount of force. The final question asks for the time it takes to rotate this massive stone, which was initially at rest, 1 full revolution. This problem is the same type as the one we just solved. It's a type that uses the two ways to calculate torque and rotational motion, namely torque from a kinetics perspective and a kinematics perspective. First, since the force and the distance from the axis of rotation are given, the torque from a kinetics perspective is 45 Newton-meter according to the formula. Here, we will assume the angle between the force and the axis is a right angle. Now, let's think of the same torque in terms of the relationship between the moment of inertia and angular acceleration from a kinematics perspective. The stone can be modeled as a solid sphere, and according to the formula, the moment of inertia is 2,656.8 kilograms meter squared. Therefore, by the kinematic torque formula, the angular acceleration is 0.01694 radian per second squared. Now we use the relationship between angular position, angular velocity, and angular acceleration. 1 full revolution is a change in angular position of 2 pi, and since it started from rest, the initial angular velocity is 0. Therefore, according to the formula, the time it takes to complete 1 revolution is 27.24 seconds. So far, we've solved a few representative types of rotational dynamics problems. Even complex problems in rotational motion can be solved without much difficulty if you properly apply the two methods of calculating torque, kinetics and kinematics, and the kinematic relationships between angular position, velocity, and acceleration. Please practice a bit more on your own through other similar problems. That's it for today's lecture. You all did a great job. I'll see you next time.